we've dealt with this formula for arc length and everything we've done so far, but the title of the section is arc length and surface area. So we have one more topic to discuss, and that's going to be, well, what happens if we have a graph of some function and we aren't concerned with just finding the length of this, but what happens if we take this curve and rotate it around the x-axis, let's say. So we get some solid revolution. This should feel very familiar from Chapter 6 stuff. But now, instead of, asking you what's the volume of the solid, that's a great Chapter 6 question. But the question now is going to be, what is the surface area of this solid revolution? So it's going to be very, very much like our previous formula for arc length. We're going to take this curve, rotate it around, and instead of finding arc length, we're going to find the surface area. So if you see this is not something that you just go back to 6.3 and 6.4. This is going to be a new formula we're going to come up with. And so let's work on driving the formula together. So suppose that here is a function f of x. So as usual, we're going to kind of break it up into chunks. And so we know from before that, like this chunk here, let's call this chunk L sub I for the ith chunk here, this length is going to be approximated by the square root of 1 plus f prime of ci squared times delta xi. So here, this is our Li. This down here is delta xi. Ci is some point in between here. So this is based off of what we had before, back in the very first set of videos. The length here is approximated by this square root times the length of that line segment. Now, what happens if we have this as the length of our line segment, and we form a cylinder here? What's the area? What's the surface area of this cylinder? Well, it's going to be, so we're imagining this as a perfect round cylinder, and it has parallel edges here. So we're kind of flattening this out in our approximation. The radius here is f of ci, that's the height right here. And so surface area of a cylinder, of this side of the cylinder, we don't have to worry about the holes on either end, is going to be the area of the circumference of the circle, which is 2 pi times f of ci times the radius. And so, times, that's the radius there. And that is the height, the width, whatever you want to go there for the cylinder. So when we put these pieces together, 2 pi times f of ci times, what is Li from up here? Square root of 1 plus f prime of ci squared times delta xi. So this is going to be our approximation for what's the surface area for when one little chunk of this one little chunk of this graph is rotated around. And so then what happens is, when we want to find the overall surface area, we want to integrate this over the corresponding bounds. That becomes a dx, and the f and f prime just become f of x and f prime of x. And so all of that gives us all of that gives us this formula here for the area of a surface of revolution. So assume that we have a non-negative function whose derivative exists and is continuous on the interval from a to b. The surface area S of the surface obtained by rotating the graph of f about the x-axis between a and b is 2 pi times the integral from a to b of f of x times the square root of 1 plus the derivative of f squared, and integrate that with respect to x. So that is this formula, and we'll for the other half of this section of the textbook, and we will spend the rest of the section. We'll spend the rest of the section applying this formula.